In the first part of this introduction to standardized echography, we will be dealing with basic physics and technology, as well as with the importance of standardization. First, what is ultrasound? Ultrasound is sound, but with a frequency above 20 kilohertz. What are kilohertz? What are hertz? The number of oscillations per second. 1 hertz is 1 oscillation per second. 1 kilohertz is 1000 oscillations per second, and 1 megahertz is 1 million cycles or oscillations per second. In ophthalmic echography, frequencies between 8 and 50 megahertz are being used. And here a graphic display of such an oscillation. When we look at the baseline here, the time base given in microseconds at the bottom, and the ordinate, the amplitude in millimeters, then we see that a particle oscillates up to a positive maximum amplitude, down again through the baseline to a maximum negative maximum amplitude, and so on. It's one particle that shows these oscillations, and the shortest time between the same phase of this oscillation, for instance, between the negative maximum and the next negative maximum of this oscillation, is called 1 cycle, or between the baseline to the next baseline reached in the same direction, 1 cycle, or the shortest interval between the maximum positive amplitude and the next one, that is 1 oscillation. Ophthalmic ultrasound is a mechanical energy. It requires liquid or solid media to occur and to spread. It cannot occur or spread in gases, in air. That's true for the ultrasound used in ophthalmology. And here a graphic display of the progression of these oscillations. One particle gives the energy to the next particle in the medium, and so on. This way a wave originates, and the wave is characterized by lambda, the wavelength. It is the shortest distance between the two particles that are in the same phase of oscillation. For instance, the negative maximum amplitude, the baseline, or the positive maximum amplitude. That's the wavelength, and it's given in millimeters, whereas the distance within the medium is given in meters, and the amplitude again in millimeters. The wavelength lambda plays an important role. It is a function of the frequency of ultrasound, F, and also a function of the velocity of ultrasound in the medium, V. And here is a formula that we should remember. lambda is directly proportional to velocity and reversed proportional to the frequency. For 8 MHz ultrasound, the wavelength is 0.19 millimeters in regards to the velocity in tissues. For 50 MHz, the wavelength is much smaller, 0.031 millimeters, again in relation to the velocity in tissues. And when we look at this formula, we see that the higher the frequency f is, the smaller becomes the wavelength. And a smaller wavelength, of course, means a greater resolution. Therefore, we try to apply the highest possible frequency when we examine the eye and orbit with ultrasound. Because the absorption increases and as a consequence the penetration into the tissues decreases with increasing frequency, the increase in frequency and consequently the resolution are limited when examining the eye and orbit. In standardized A-scan, the entire eye and entire orbit is being examined, the entire orbit including the orbital apex. For this standardized A-scan we use 8 MHz effective frequency. That is the frequency that is emitted by the probe, not the frequency that is built into the probe. When we use low frequency B-scan to examine the entire eye and the anterior orbit, 10 MHz are being used. When we use 20 MHz B-scan, only the most anterior orbit may be examined together with the entire eye. And when we use the UBM B-scan, the B-scan by microscopy with 50 MHz, only the most anterior portion of the anterior eye segment may be evaluated. That means the cornea, the anterior chamber, the iris, and the anterior lens surface. These frequencies in B-scan are not effective frequencies, like the 8 MHz for the standardized A-scan, but nominal frequencies. These are the frequencies that are built into the probe. But the effective frequency then is 1 to 5 MHz less than indicated. For instance, when we use a 50 MHz probe, the sound velocities depend on the acoustic properties of the medium. Generally, we assume in tissues of the eye and orbit a velocity of 1550 meters per second. We do not know the precise velocities in various tissues as they cannot be evaluated in this regard while in a living stage. We know, however, the exact sound velocities of vitreous and aqueous humor to be 1532 meters per second and of the normal human lens to be 1641 meters per second. These two values were found by the Swedish researcher Jansson in the 1950s. Bone has a much higher velocity than the soft tissues of the eye in orbit, 3,300 meters per second. It's important to realize that metals, glass and wood, the materials of foreign bodies in the eye, have much higher velocities ranging from 2,000 up to 7,000 meters per second, where silicon oil has a very low velocity of only 980 meters per second. The distance measured with echography is given in this formula. It's directly proportional to the velocity in the proper medium and the time, the running time of the ultrasonic pulses until they return to the probe as echo signals. The distance is given in millimeters, the velocity in meters per second, the running time of the ultrasonic pulses in microseconds, in millionths of a second. Now the question why divided by 2, that comes from the fact that in echography of the eye and orbit we have to let the ultrasonic pulses run in one direction to the target and then await their return to the probe. So the ultrasonic pulses run through the distance twice, and therefore we divide here the distance into half. And now the question, how does echography work? An echographic instrument has a generator that produces high-frequency electric pulses. And they are emitted through a high-frequency cable and reach the probe. The probe has a transducer that transforms the electric into ultrasonic mechanical pulses and emits them as beam towards the tissues. Such an emitted pulse has a duration of only very few microseconds, and about 1,000 pulses are emitted per second. That's very important that we get on the display finally a standing picture, not a vibrating, oscillating picture. In the tissues, we're dealing with absorption that weakens the ultrasonic pulses as they continue to travel. On the other hand, very important, the tissues produce, through reflection and scattering, the echoes. The echoes are the carriers of the ultrasonic information that return to the probe and are transformed by the transducer into electrical signals. The echoes are received during the breaks in the pulse emission, which is about 1 millisecond, in order not to interfere with the transducer that emits and receives. The electric signals are then, through the same high-frequency cable, transported to the receiver. In the receiver they are amplified, and then finally they are processed, again specific amplification, and displayed as B-scan or A-scan. And then we have on the same screen first the B scan, and then when we switch to A scan and switch the probes, then the A scan. Now the formation of echograms. The high-frequency electrical and mechanical pulses have a duration of only a few microseconds. In the breaks between the pulses, which are milliseconds duration, echoes are received, and the ultrasonic energy therefore is minimal and requires a tremendous signal amplification by the receiver and during the signal processing in order to display echograms. Standardized A scan and B scan echograms are displayed on the same screen, one after the other, not simultaneously, successively. And standardized A scan and B scan require separate probes and a very different signal processing to be optimal. We will talk about this when we talk about B scan and A scan. And here two examples of ultrasonic probes. On the left side, the standardized A scan probe that emits 8 megahertz. It has a diameter of 5 millimeter and emits a parallel beam. On the right side, a 10 megahertz B scan probe. The B scan probe has to be larger than the A scan probe because in the B scan probe the transducer has to travel to create an acoustic section for this two-dimensional display of B scans. "50 megahertz probes for the anterior eye segment." It all started with the original UBM probe that was open and only for immersion technique. Here you see the transducer on the tip of the probe. This transducer was shifting back and forth quickly in front of the cornea, and one had to be very careful not to touch the cornea. Aviso S probes by Quantel Medical, the modern UBM probes, are closed or open. Here is open for immersion, here is closed for contact. And now to the echography in ophthalmology. There are basically three methods. The most widespread method in the past decades was the A-scan biometry for axial eye length measurements prior to cataract extraction. This required cheaper, simpler instruments that were not useful for any diagnostic purposes rather than the measurements. Then there was diagnostic B-scan echography with or without simultaneous vector A-scan. We will talk about this in chapter 11 of the introduction. Or with or without three-dimensional display. And then we have the standardized echography, which is both diagnostic and biometric, an optimal combination of standardized A-scan 8 MHz and standardized B-scan 10 to 50 MHz. This is by far the most effective and capable echographic evaluation of the eye and orbit. And in this course we only focus on this. And then the question, what is standardized echography? The basic concept is a combination of real-time standardized B-scan, 10 to 50 megahertz frequencies, and real-time standardized A-scan, 8 megahertz frequency. Real-time meaning, in contrast to the conventional CT scan and MRI, we look at the echograms as they are dynamic and change with changes of the probe position of the eye, gaze direction, and so on. Pulsations are being seen and so on. That is real time. That's one of the great advantages of standardized echography over those radiological methods. And now the question, what is standardized echography? It has first a specific, unique design of instrument, probe, and signal processing for the A-scan, for the standardized A-scan. And secondly, of the examination techniques for both A and B scan, a specific, unique design of the examination techniques as well. And then we have a specific optimal design to achieve optimal echographic localization, tissue differentiation, and measurements. Second, standardization of this optimal design for both A and B scan. A scan instrument, signal processing, etc. B scan examination techniques in addition to the A scan. With this standardization, we speak one echographic language. That's extremely important. It doesn't depend on the instrument, it doesn't depend on the probes, what the result is. And so we obtain reliable, understandable, comparable, and repeatable results that in addition are optimal. That's standardization. And standardized echography is the method of choice at all levels of performance. When it is to rule out a pathology in the posterior eye segment in a case of dense cataract or anterior segment hemorrhage, the method of choice is standardized echography. When it comes to measurement of extraocular muscles and to grading of Graves' orbitopathy, the method of choice is standardized echography. When it comes to tissue differentiation, to the diagnosis and differential diagnosis of a malignant melanoma, for instance, or a metastatic carcinoma of the choroid, all these tasks are done with standardized echography as the method of choice. And why should we use standardized echography? Now comes the answer, what I have already mentioned, that it gives us the best results. All intraocular lesions that are larger than 0.2 millimeters can be detected. and all orbital lesions which cause clinical signs and/or symptoms can be detected. And with standardized echography, more than 75 different intraocular lesions, types of lesions, can be differentiated. And more than 65 different orbital lesions can be differentiated. More than 99% correct results in the differential diagnosis of intraocular lesions in a number of conditions: vitreous hemorrhages, retinal detachments, cystoid macular edema, intraocular tumors, endophthalmitis, episcleritis panophthalmitis, traumatic lesions, foreign bodies. More than 99% correct results over several decades of evaluation. Or in the orbital and periorbital lesions. Endocrine orbitopathy, more than 99% correct differential diagnosis. Orbital myositis, papilledema. Not quite as high, but still outstanding, orbital cellulitis, abscesses, vascular lesions like AV fistulas, optic nerve lesions, tumors and pseudotumors, above 80% correct differential diagnosis, traumatic lesions, foreign bodies. There is no other examination technique or method in the orbit that can come close to that. Now we have to consider the following. B-scan, whether it's used with or without the so-called vector A-scan, usually allows only for soft diagnosis. I would call them plus minus. For instance, suspected to be this lesion, or it's possibly this lesion, or it looks like this lesion, could be this lesion, maybe sometimes even probably is this lesion, but soft diagnosis. In contrast to that, the standardized echography, which combines the B-scan with the standardized A-scan, it provides hard diagnosis, 1+. More than 99%, we may call it just pathognomonic for or proves this lesion. If it's more than 90%, then we can say typical for or corresponds to that lesion. But that's the difference between standardized echography and B-scan. Besides the quantity of the information we get from both techniques, standardized echography provides 100% of the possible differential diagnosis ophthalmology. And here a graphic example of results from the 70s to 90s in the eye department in Iowa City at the University of Iowa. We see here in red standardized echography, hard diagnosis, 1+. Here almost 99% reliable, correct differential diagnosis in retinal detachment, in tumors, intraocular tumors, endophthalmitis, early endophthalmitis, that is hemorrhage. And then when we look at B-scan alone, a weak soft diagnosis of about 80% in retinal detachment, much less in tumors and endophthalmitis, early endophthalmitis, and more than 80% in hemorrhages. But that's the difference between standardized echography, both A and B scan, and B scan alone in the eye. And in the orbit, even more pronounced differences. Graves' orbitopathy, for instance. B scan soft, and in a small amount of the cases, A scan strong, hard, 99%. Optic nerve lesions, optic nerve compression, and tumors of different kinds. That's why we use standardized echography. Now, knowing and understanding the tools and rules of standardized echography plus experience leads to the best diagnosis. But because the knowing and understanding is so important and outrules the experience, it is very important for you to follow during this course all the important teaching that we give on that. Possible only with fully standardized instruments and examination techniques. That is important.